All right. Let's look at the coin flip worksheet. So each of you need a coin, and you're going to play 10 rounds flipping coins. And each round, or sorry, 16 rounds. Each round is going to be 10 flips. So you flip a coin 10 times, you count how many heads you had, and then you enter that in round 1. Then you flip the coin 10 more times, and you count how many heads there are. Maybe you want to use tally marks, some other method. You'll put that in round 2. Once you have completed all 16 rounds, go to the Emory High Canvas page, and there will be a Google form called Coin Flip, and enter your data for all 16 rounds. Now I realize you're flipping the coin 160 times. I'm sorry. That's just how we're going to gather data. Once you have entered this into your Google form, you can answer these 7 questions on the first page. Now some of them you might struggle with a little bit. So I'm going to pause the video and you guys flip the coins. Once you have all of your coins entered into the Google form, then go ahead and start answering questions 1 through 7. Okay, welcome back. So, question 1, how many heads would you expect in each round? 5. There's a 50% chance of head, that's if the dice or the coin is fair. So you should expect 5 heads per round. Okay? So, what is the average number of heads in your 6 rounds? So you just need to go through and add up all of your rounds and divide by 16. Okay? The number should be somewhere close to 5. Did anybody get 5 exactly? No. Did anybody get less than 4? Did anybody get greater than 6? So everybody's between 4 and 6. Okay. All right. Now, standard deviation. That pesky little calculation. So let's suppose that my average was 5.23. Okay? And I had the following. Oh, no, he's on his phone. Oh, I have calculators for you. You don't need to use that anymore. Everybody wants a calculator all of a sudden. Yours was exactly 5. Nice work. Next time, use one of my calculators. So, what if I had the following rounds? 6, 5, 5, 8, 2, 4, 3, 3. How do I calculate the standard deviation? Well, first, let me show you that nasty formula. Okay. So the formula says S, which is a sample standard deviation, right? If you flip the coin an infinite number of times, then you can call it a population, a parameter. But we're taking a sample, so we're going to use the formula for the sample standard deviation. It says take every term and subtract from it the average. Okay? So I need to go through and figure out how far is each number from the average. Okay? So how far is 6 from the average? I'm gonna make this a little bit easier for me. I'm gonna say 5.5. How far is 6 from 5.5? 0.5, positive 0.5. And in this class we always do value minus average. How about 5? Negative 0.5, and 5? Negative 0.5, and 8? Positive 2.5, and 2? Negative 3.5, and 4? Negative 1.5, negative 2.5, negative 2.5. I probably need some bigger numbers in here. So let's do a 9 and a 7. 9 is 3.5 and 7 is 2.5. 1.5. Sorry. Okay, those are my differences. If we go back to the formula, what do I do with my differences? Square them. Why do we do that? We need to get rid of the negatives. So I go through and square every difference that I have. So that's 0.25, 0.25, 0.25. I won't be able to do these in my head. 6.25, 12.25, 2.25, 6.25, 6.25. Do I already have a 3.5? Yeah. 12.25 and 2.25. Okay, now we look at the formula. What does it tell us to do now? Sigma. Giggle, giggle, giggle. You guys love that. So capital sigma in mathematics is the summation machine. It's the letter capital S in Greek, and it says add up everything that you have. So I'm going to go to here and just add all these together. So 0.25 plus 0.25. Okay, and that gives me 46.25. All right. And I look at the formula now, and it says divide that by n minus 1. Now, if this was a parameter, we would divide by n, because we're essentially taking the average. But because this is a sample, we want a standard deviation that's a little bit larger than it actually is, just to make sure we don't mess anything up. So instead of dividing by 16, I'm going to divide by 15, and that will inflate my SD just a little. So I take that number, and I divide it by 15, and I get 2.82. Now yours is going to be different, obviously. What does this number tell me? That is the average distance from the average. Now, truth be told, it's a little bit bigger than the average distance from the average, but that's the number we're going to use. Okay? So this is the average distance from the average. So, if we go back here, I had 5.5 as my X bar, and I had 2.82 as my SD, my standard deviation for sample. Okay? So, what should I consider as an ordinary number of heads? Well, most people will be between X bar plus or minus S. Oh, sorry. Do you need some help? You good? Oh, you're not in trouble. I just wanted to help. Okay. So if I take 5.5 and I do plus or minus 2.82, so 5.5 plus 2.82 is 8.32, and the other end, 5.5 minus 2.82 is 2.68. Okay, that means the majority of people who play this game should get somewhere between 2.68 and 8.32 heads. Was your SD significantly smaller than that? Okay, good. mine's actually kind of big. Your SD was 6.4? I think you messed up. You might want to try that again. So one thing that you have to be careful about is, oh, now he's on his phone for real. So if I had -3 squared, that's 9. But if you type in -3 squared like this, you're going to get -9. So when you do this squaring, I would just ignore all the negatives because they're going to go away. So when you find your distances, oh, you want to let him in? When you find your distances, because we're going to square them, we don't actually need the negatives. So we can just ignore the negatives the whole way. Hey, guess what, guys? I know where my problem is. I know why my SD is so big. Look right here. I did not take the square root. So, yeah. So I forgot to take the square root, so 2.68, take the square root, and I get 1.63. That sounds much better. Okay, so that means on number 4, I should get 5.5 plus 1.63 or 5.5 minus 1.63. That gives me an upper bound of 7.17 and a lower bound of 3.87. Okay? But did I really expect, oh, sorry, I'll wait for a second. I'm going a little too fast. Okay, did everybody get an SD that sounds better now? I don't know, you got a different SD. You don't know what it means? Okay, that's fair. So, look at this. Is that really what I expect? Did I really expect 5.5? No, I expected 5, didn't I? So, should I do 5 plus 5.5 plus 1.63? Or does it make more sense to do 5 plus 1.63? Because we're assuming that the coin is fair, right? And that's how we're going to set up our null hypothesis here in a minute. So actually, I should do 5 plus or minus 1.63. Do you guys need help? So, so the expected number of heads is 5, right? And most people will be within this number. So we shouldn't add this to our average because our average isn't going to be perfect. So this number is our average distance from the average. And this number is how much we expected to get. So if I add that up, 5 minus 1.63 and 5 plus 1.63, my answer for number 4 is 3.37 to 6.63. Okay? Whatever. Don't worry about it. I don't believe in busy work. I'm here to teach. I don't care. I don't care too much about erasing and rewriting that. Okay, so does everybody get that? According to my data, which I made up, most people should fit in this window, 3.3 to 6.6, right? Which basically means 4, 5, or 6. Most people who play this game should get 3 or 4 or 5 5s. Does that make sense? Well, let's look at the class data and see what happened. is it? Coin flip data. So here is the class data. My histogram has really weird numbers. But is that normally distributed? It's pretty close, right? That looks pretty normal. There is a little bit of a long tail on that right side. Does it look like most people scored 3 or 4 or 5 points? Yeah, it does. Okay, so that is sort of a usual outcome. So if you play this game by flipping a coin 10 times, what do we think is going to happen? You're probably going to get a 3 or a 4 or a 5. Or sorry, that's not what I meant. A 4 or a 5 or a 6. Did anybody get scores outside of that range? Yes, they're just less common. Okay, so let's go back here. What should you consider as an unusual number of heads? So I'm going to take 5, and I'm going to add what? 2 standard deviations. So 2 copies of 1.63. So 5 plus 2 times 1.63 gives me an upper bound of 8.26. And then the same calculation with the subtraction gives me 1.74. Okay. What do these numbers tell me? What about them would be unordinary? If you landed in that window, it's going to be unordinary. If you're outside that window, something is seriously wrong. Right? Now, can a perfectly fair dice create results that are outside the window? Yes. It's just not common. So if we look at our histogram, so it's basically less than 2 and greater than 8. Are there any scores 2 or below or greater than 8? Yeah, there are some, but not very many. There were none over here. Nobody got less than 2, right? And then there are a handful over here, but not very many. So if you were the coin manufacturer for the casinos and you're flipping coins, if you get 0 or 1 heads, you should probably throw that coin away. Could you be throwing away a perfectly good coin? Yes, you could. But chances are something's wrong with it. If you get 8 or 9 or 10 heads, you should probably throw that coin away. I guess 9 or 10. If you get 9 or 10 heads, you should probably throw that coin away. Okay? Or take it home with you and win money off your friends. Okay. Does that make sense? That's how statistics works. Okay? So we're going to look at all of this data in a classroom setting. So let's go back here. So you're going to count how many of your rounds were ordinary and how many were unusual. And just a reminder, what percentage of our games would we expect to be ordinary? About 68%, according to the normal curve. Okay? About how many would we consider to be unusual? Well, 2 SDs gives me a 95% window, which means these 2 tails add up to 5%. So about 2/3 of the time, you should be within 1 standard deviation. And about 5% of the time, you should be outside of 1 standard deviation. Okay? All right, next page. All right, so let's go to our data. How many rounds were played total? Let's see. Somebody turned in a blank number. I'll find it. I guess I could use this. Oh. All right, so that's row 287. but there's a header row, so 286. So total, we played 286 rounds. All right. Okay. Question 9. What is the class average for the number of heads rolled? So I'm just going to ask, I've got to do this for my computer. So I want the average of column A. So the average is 5.12. Okay. Now, I want you guys to calculate the standard deviation. Gavin says no. How awful would that be? Very awful, right? We would have to find out how far is each number from 5.12, square them, add them all together, divide by 285, and then take the square root. So I'm not going to make you do that. So this is average, and this is standard deviation, and through the miracle of spreadsheets, and again, I want the sample standard deviation, not the parameter. So the sample standard deviation of A gives me 1.6. So my average is 5.12, and my standard deviation is 1.6. Okay. Looking at coin flip. How many heads are expected in each class round? 5. So this is 5.12, and this was 1.6. And this was 286. What would we consider as an ordinary number of heads? Well, are we going to base ordinary off of my sample average or the expected value? The expected value. So this will be 5 plus or minus 1.6, which is 3.4. 3.4 to 6.6. Okay? So how many of the classrooms, how many of the class rounds should we consider as ordinary? So let's go through and count. So, okay, so we're counting the 4s and the 5s and the 6s, right? If I can do this, again, I'll use my computer. So the 4s start on 47, and they end on 230. So that's 183. So we had 183. What is that in a percentage? So 183 divided by 286 is 64%. Okay, looks like we are finishing this next time. See you guys.